Okay, this is just a short presentation on how to work with calculations that involve light. Um, we we need to just remember a few things about light. The first important thing to remember about light is that it always travels at a constant speed. That speed is 3 times 10 to the 8th meters per second. So anytime you're using an equation that uses the letter c, they're referring to this value, 3 times 10 to the 8th meters per second, the speed of light. The other thing to remember about light is to understand its different properties of its waves. The first property is that we talked about was called frequency. And frequency is defined as the number of waves that occur in 1 second. Okay, and then the other property that we talked about in our calculations was wavelength. We define wavelength as the distance between two peaks of a wave. So if you see the image here on the side, you can see that the two, frequency and wavelength, these two properties are inversely related. That means that when one goes up or becomes higher or greater, the other one goes down or becomes lower. So if you look at the red wave on the top, you'll see that it has, out of all the waves there, it has the longest wavelength. The wavelength distance between two peaks, so the peaks are spread out the most. So as a result of that, you can't have as many waves per second because the waves are further spread out, so you find that the frequency is lower. And then compare that to the very bottom one where you have a short wavelength, right? The distance between two peaks, and it's inversely related with frequency. Look at how many peaks or how many waves that you get in that one block of time. The third property that we talked about was amplitude, and we're not going to do any calculations dealing with amplitude here in high school chemistry. But we define it as the height of a wave from rest position. You can kind of think of amplitude as, for instance, intensity of light, kind of how bright it is or how many photons of light are being produced. Okay, other reminders, now that we've kind of defined wavelength and frequency, let's talk a little bit more about how they show up in equations. Wavelength is usually replaced with the Greek letter lambda. It kind of looks like a flipped upside down Y. And while it's tough to write lambda if you're just using like a keyboard on a phone or a tablet, some people will put a Y in there or type in wavelength itself. Please know that the units for lambda or wavelength is in meters. So occasionally, like you saw on this slide right here, these wavelengths are listed in nanometers, nm. In order to do work and calculations with these numbers that are nanometers, you'll have to convert them into meters, and you do that by just dividing by 10 to the 9th power. And that'll get you, that'll convert it from nanometers into meters. The second term that we talked about, frequency, it also gets its own Greek letter. It's the Greek letter nu. It looks like a cursive V. So whenever you're using, for instance, your phone or like just a standard tablet keyboard, most people replace this with the letter V. But the reason they do that is so that it doesn't get confused with other science concepts that deal with V, like in physics, V stands for velocity. So they try to separate things, and that's why you start seeing a lot of these Greek letters in there. The units for frequency, it's hertz, Hz. You will see, depending on the textbook, depending on your professor or your teacher, you will see hertz expressed in a number of different ways that all mean the same thing. Right? We said that frequency is how many cycles there are, how many peaks there are per second. This can also be expressed as 1 over seconds, right? That's a per second. A second to the -1 power, or -1 afterwards, is a per second. Some people even call it inverse seconds. So they all refer to the same thing. The SI unit that we use is called hertz for that. Okay, here's our first equation that we use for light calculations. It is C equals lambda nu. Okay, we've defined what each one of these are, C and lambda and nu. But for please realize C, the letter C, is used to represent the speed of light. That number, 3 times 10 to the 8th meters per second, it is always going to be 3 times 10 to the 8th meters per second. That's what C is represented by. So, and you might have heard like E equals mc squared, Einstein's famous energy equals mass times the speed of light squared. Yeah, that C there refers to the same thing, the same number in that C squared is 3 times 10 to the 8th meters per second. And that's a constant, right? It's the speed of light through a vacuum, and it's not going to change. You will use this in every light calculation. C will always represent 3 times 10 to the 8th meters per second. Okay, so if you substitute in 3 times 10 to the 8th meters per second, you get that equation that you see on the bottom right. 3 times 10 to the 8th meters per second is always equal to the frequency of a particular type of light times its wavelength. Right? Always. So lambda times nu, when we're talking about light, just light now, lambda times nu will always equal 3 times 10 to the 8th meters per second. So when do you use this equation? Well, you're going to have to read into the problem to find out what they're asking you to solve for and what information that they give you in the problem. So if the problem gives you a frequency and asks you to solve for a wavelength, that is an appropriate time to use this equation. Okay, so it gives you a frequency, asks for a wavelength. In order to solve for that wavelength, you're going to have to rearrange that formula, C equals lambda nu, so that you're solving for wavelength. You can see in the bottom left the result of rearranging this equation. Lambda is equal to C, the speed of light, divided by the frequency nu. Right? And if you do that, if you just plug in 3 times 10 to the 8th meters per second and divide it by the frequency that's given to you in the problem, your answer will be the wavelength. Okay, and if we go to the right side, if your problem gives you a wavelength, but then ask you to solve for a frequency, and it's just the same thing. You're just solving for a different variable in this equation. So you'll use C equals lambda nu, but this time, instead of rearranging for wavelength, you'll be rearranging to solve for frequency. It looks very similar. In both cases, we're taking the speed of light and dividing by the quantity that they give us in the problem. And when we hit enter, it will spit out the other quantity. Remember, your units for frequency will be in hertz, and your units for wavelength will be in meters. Okay, here's our second equation that we use for our light calculations. It's pronounced E equals H times nu. Right? E is representative for energy. Again, remember in Einstein's E equals mc squared. We have E there as well, and that's what it stands for. It stands for energy. The units that we use for energy in chemistry are joules, and we can convert between joules and probably a unit that you're used to, calories. Energy is, or the letter E is used to represent energy in this formula. Here we see nu again, right? The frequency in hertz, that is the same. There's nothing different. Frequency is there. It's just H is in here now. Now, H just is a constant. It's called Planck's constant. It's named after the person that came up with the number and kind of discovered this. They were doing some pretty cool experiments in the early 1900s, late 1800s, and they came up with this value. And they found that whenever a certain frequency of light existed, that it was proportional with the amount of energy that light had. So whenever we see H in this equation, it will always be 6.626 times 10 to the minus 34th joules seconds. Okay, yep, and those are the units. You see that JS, that is a joule second. Okay. It's a constant. It doesn't change. So anytime that you need to use this equation, E equals H nu, or H times nu, you can think of it as E equals 6.626 times 10 to the minus 34th joule seconds times the frequency. Okay, that will give us the energy of that light. Okay, so when do you use it? You're going to have to read the problem and figure out what the problem is. Not only what is the problem giving you, but what is it asking you to solve for? In this case, a lot of problems will say, hey, how much energy is in a photon of this color light or this frequency light? And they'll just give you the frequency in hertz. This calculation isn't very complicated, because normally that's the case. They'll give you the frequency, and all you have to do is kind of plug the frequency in for nu, and then multiply it by 6.626 times 10 to the 34th, the minus 34th, and there you go. You have energy, and that energy is in joules. And that's it. Those are your equations that you use for light calculations.